Hello everyone and welcome to this presentation on Gain PPA Advantage, a new aging-aware STA solution for high-performance semiconductor designs. This is a joint presentation by ARM and Cadence. I am Satish Balasubramanian from ARM doing the presentation. My co-author is Paddy Mamtora, Senior Director at Cadence. Here is the outline of our presentation. We'll start by understanding what the aging problem is and understand why we need an aging solution. Then we look at techniques that have been used in the past to deal with the aging problem. Then we'll introduce the new aging-aware solution from Cadence and get an overview of both the characterization as well as the Tempest timing methodology. Then we'll go through the evaluation results from ARM and understand both the accuracy as well as the PPA impact and runtime impact of the new solution. Then we'll look at the benefits to mutual partners of both ARM and Cadence as a result of using this new solution. We'll conclude by going through the summary. Introduction to aging. Aging is a reliability phenomenon by which transistor voltage or VT degrades with time. This VT shift or the VT increase leads to reduced device speed as time progresses. Aging has always been an issue ever since we have been using CMOS transistors. However, with reducing supply voltages or VDD, aging is becoming an even more critical issue, especially in mission critical applications like the automotive and server space, where enhanced robustness of SOCs is paramount. Aging is becoming a critical issue. Even for mobile applications where the lifetime of the SoC device is smaller compared to server applications, aging is becoming a critical problem due to reduced VDD. Aging is a phenomenon that happens because of two different mechanisms. One is called hot carrier injection or HCI. The other phenomenon is bias temperature stability or BTI. While both these factors, HCI and BTI, lead to device degradation, typically it's a BTI which has a bigger impact. In the past, the aging phenomenon was only seen as a timing degradation. However, in the recent past, with reduction of supply voltages, we see a lot of interdependence between reliability and PPA. Aging causes a timing problem. This timing problem causes a voltage shift. Hence, you need to probably apply a higher voltage to get the same performance. This causes a power problem, which in turn leads to a thermal problem. And that's the interdependence between reliability and PPA. Now let us understand the impact of aging by looking at some common mission profiles. On the left, we plot aging versus VDD, looking at a 5 nanometer technology. We have kept the mission profile constant at 10 years, 1 volt, 105C, and we have simulated critical paths across multiple STA voltage conditions. As you can see, at 0.5 volt and 0.6 volt, the impact of aging can be significant. You see anywhere between 5 to 7% impact on critical paths on account of aging. The impact of aging tapers down as you go to higher voltages at this particular mission profile. So this just points out that even for devices that operate at a lower voltage, aging can be a critical issue. On the right, we plot aging versus operational time or the aging time. We have assumed an aging mission profile to be 1 volt 105C. The STA condition or the voltage condition is 0.615 volt. The temperature was minus 40C. And what we have plotted is the impact of aging as time progresses. So you can see the aging impact at 1 year to be about 5 to 6%. And when the device is operational at 10 years, the aging impact is about 8%. So the aging impact increases with time, as this chart shows. And that's the reason why devices in the automotive and server applications are more prone to aging. Now let's understand what are the past techniques that have been used in the past to deal with the aging problem. As we have seen in the previous slide, the aging degradation depends on the stress profile, which is the stress voltage, the stress temperature, duty cycle, activity factor, and the aging time. Some previous solutions that have been used to deal with the aging problem include generating an age library, where you take a library and then set a certain stress profile to all the cells in the library, characterized with that stress profile. This age library is then used in STA or timing closure. The issue with this approach is, in STA we have assumed that all transistors and all cells in the library have exactly the same stress. Unfortunately, this doesn't work accurately when you have clock gating, when you have different duty factors, or when you have multi-voltage domains. This solution is also impractical from a high cost point of view because you have to characterize several mission profiles and you have to use several Liberty files for multiple mission profiles. So it becomes unmanageable with both characterization as well as timing closure. Flat derates is another technique that has been used to deal with the aging problem. Flat derates unfortunately don't work very well because if you used a very pessimistic derate, you have a silicon loss. I mean, you have a PPA loss to the SOC. On the other hand, if you used a very optimistic derate, you could have a PPA loss on silicon. Some SOC designers have also run RHEL expert simulations on top critical paths. Unfortunately, the problem with RHEL expert simulations is even though they're very accurate, it is not practical to run RHEL expert simulations on all paths. Plus, if you simulate the first 50,000 paths with RHEL expert and assume you have covered the problem, it may not be very accurate because you will realize that paths which were not critical with fresh silicon suddenly become critical once they are prone to aging. So that is the issue in running RHEL expert simulations on a limited set of critical paths. With that background, let's now introduce the new aging-aware solution from Cadence. The new aging-aware solution from Cadence is a combined Liberate plus Tempest solution. We'll use the updated Liberate tool to generate aging models. And there'll be a single model that supports multiple stress conditions. So depending on the SOC needs, you could model multiple stress profiles as per the needs of the SOC and then dump out one single model that has all these mission profiles. There is no assumption on duty cycle that is needed during the characterization. Similarly, there is an update to the Tempest STA solution as well to deal with aging. The new solution models instance-specific aging. So depending on the voltage domain, a cell or instance is present, uh, that stress profile is included in the aging analysis. Similarly, the duty factor is also included in the aging analysis. In the past, characterization solutions have assumed the stress to be same between the mission profile and STA, whereas the current solution does not make that assumption. You could have multiple stress profiles and they can be different from the STA condition. Also, SOCs just don't go through a single mission profile through their life. They go through multiple mission profiles or what we call the multi-segment stress. The new solution allows for that analysis also to be done. We have seen that the cost in terms of both library characterization as well as STA timing closure is affordable, and we'll look at data in subsequent slides. The new framework of Liberate and Tempest also supports automated SPICE-based accuracy validation at both the cell level and path level. It is possible to dump out critical SPICE decks of critical paths and then run RHEL expert simulations and understand the accuracy between ST and SPICE with this new tool. Let us now go through the Liberate updates for aging in more detail. Typically, we use the Liberate tool to characterize nominal and LVF data. So you have a characterization collateral. Then you use the Liberate tool to generate nominal and LVF data across multiple STA conditions. And what the output of that flow is a fresh Liberty file. The setup for aging is very similar to what we use for the nominal and LVF characterization. You just need two extra set of inputs. One is the aging PDK to characterize aging. Typically, foundries have the aging models as part of the regular PDK. Then you need to understand the mission profiles that are applicable to your SOC. So you need to understand the ranges of VDD stress, the range of temperature stress, and the range of aging times, and include them in the aging model characterization. So once you give these inputs, you have a aging Liberty file that is generated for each STA condition. And while the tool supports multiple mission profiles, the tool also has the capability to run interpolation between aging profiles. So if your SOC has a mission profile that is not directly characterized, the tool can handle it by interpolating between existing mission profiles. The Liberate characterization flow also supports stress and recovery, but it is not necessary to have recovery as part of the characterization. It can also be used as a recovery can also be given as an input during Tempest STA closure. That would mean your libraries are generic and you don't have to hard bake the recovery information into the Liberty file. The tool characterizes all aspects of timing, including delays, slews, as well as constraints. Uh, all all PDK formats for aging, including SI to OMI, RELX per URI, and TSMC TMI SPICE models, are supported by the new tool. And the way the tool works is it takes all cells in the library, looks at all pins and when conditions, arcs, load, slews. And for each of those timing conditions, for each of the mission profiles, it computes the change in delay and the change in slew and reports them in a separate Liberty file, which is the aging.lib. We have seen that for a reasonable set of mission profiles, the characterization time is about 15 to 30% higher than what is normally taken for the nominal plus LBF characterization. Now let us understand how the updated Tempest flow handles the aging. To run aging aware timing closure, we need both the fresh as well as the age.lib that was characterized with a Liberate solution, as we discussed previously. Then the user needs to define a create aging stress profile command in the Tempest setup. And that stress can either be a single mission profile stress or it can be a multi-segment stress as we have seen previously. And the stress can be specific to each instance, like you can assign duty factors to each instance. And the stress can be different from the STA condition. And once you have the setup ready with your mission profile, then the tool uses both the fresh and the aging Liberty file. It computes delays for each instance in the design, doing a library lookup of the age.lib. Then the delays are calculated, the aging delays are calculated and propagated. Then you have an aging specific report for each mission profile. The Tempest solution supports both GBA as well as PBA analysis. And our analysis shows that there is a 10% runtime overhead in Tempest for each stress profile. And the Tempest framework also supports automated accuracy validation with SPICE. So you can dump out SPICE text. And once you have the aging report, you can also have the SPICE data and you can compare timing between ST and SPICE and make sure they correlate pretty well. And as we have seen in the past, the Tempest solution also supports multi-segmented aging profiles. Results of the evaluation. IAM has been evaluating the new Cadence offering to deal with the aging problem on a 5 nanometer node, and we'll present results, the accuracy results from the evaluation. We characterized a 5 nanometer library across multiple STA conditions and across multiple mission profiles. We then created random critical paths and then ran STA with the aging Liberty files across STA conditions, mission profiles, with recovery and without recovery. Once we got the aging reports, we dumped Spectre decks in the Tempest sessions and then ran RELExpert simulations to have the SPICE data from the aging simulations. Then we compared STA with SPICE post-aging and analyzed the error. This table gives a snapshot of results across STA PVD conditions, stress conditions, with and without recovery. As you can see, across these conditions, the min error to max error is -2 to +2%, which is a pretty narrow range. In fact, these numbers are comparable to the accuracy you would have with both nominal.lib files as well as LBF .lib files. So the Cadence aging aware solution is accurate with respect to RELExpert aging simulation. After running accuracy simulations, we then proceeded to do the evaluation on ARM core. So we used a 5 nanometer design that was closed for timing and then used the design to run aging aware timing closure. We have 3 charts here to help us understand the impact of aging on a 5 nanometer design. The first chart shows the impact to timing slack with fresh and age.libs. This chart was the original slack profile with fresh Liberty files. The slack profile on account of aging is shown with this chart. As you can see, there's a definite shift of the slag distribution to the left, or the slags become more negative due to aging impact. And the impact of aging would depend on the mission profile. In this case, we used a 5-year mission profile with recovery. The second chart shows the impact of choosing an appropriate recovery factor. Here we plotted the impact of timing without recovery and with recovery for the same mission profile. You can see that without any recovery, the timing impact could have been as high as 15%, whereas with recovery, the timing impact is about 8% on critical paths. The maximum timing impact is about 8% on critical paths. So that shows the importance of choosing a SOC specific appropriate recovery factor. To understand the accuracy of the new methodology, we did timing closure with the cadence aging solution and also did timing closure with a fixed at 10% D rate and a fixed at 5% D rate. This profile is the blue profile is with the cadence aging solution, and that shows a timing impact across critical paths. With the 10% D rate, we had a flat D rate. We had a degradation of up to 12% on critical paths. So this causes an extra PPA impact of about 4%, because with the cadence solution, the maximum impact is only 8%, whereas a flat D rate of 10% can cause a 12% timing impact. So you lose 4% PPA on account of the 10% flat D rate. Similarly, if you used a D rate of just 5% to deal with aging, you see that the maximum impact to critical paths was about 4 to 5% in STA, whereas the real aging impact was about 8%. So you would see a PPA loss of 4% on silicon. So the cadence aging aware solution is accurate, and it avoids both optimism and pessimism due to flat D rates. ARM and Cadence have been collaborating on developing an aging solution, and our collaboration continues in what we call phase 2 of the development. As part of phase 2, we'll continue the PPA benchmark on ARM cores with aging.libs across technologies, STA conditions, and mission profiles. Cadence will be working on supporting HCI. The current support in both Tempus and Liberate is only for BDI, but moving forward, there'll be support for HCI and activity factors also in a couple of months. Then we would like to explore if we can collaborate with the foundries and see if variation and aging can be co-modeled and supported in a single Liberty file. That would be advantageous to SOC designers, because that enables them to close both the variation analysis as well as aging analysis with a single Liberty file. As we have seen, recovery is critical. Choosing an appropriate recovery factor is critical. So we would like to collaborate and explore methods to provide better guidance to SOC teams on choosing appropriate recovery factors. Having seen the accuracy impact of the new solution, as well as the timing degradation on ARM cores, let us now understand the benefits of the new aging-aware solution from Cadence to the joint customers of ARM and Cadence. The previous solutions that were used to handle aging handle a small set of requirements. The aging Liberty files that were previously characterized were fixed stress Liberty files. So they assumed uniform stress for all instances, which was not accurate in a real SOC scenario. If someone used fixed D rates to deal with the aging problem, an optimistic margining would lead to risk of failed silicon, whereas a pessimistic margining would lead to worse PPA. And so the current solution supports a generic cell library that is independent of aging context. So this can be used across mission profiles. There is no assumption in terms of what mission profiles that it can cater to. Secondly, it supports interpolation across mission profiles. So even if the mission profile that is of interest to a SOC designer is not directly characterized, the tool can do interpolation between existing mission profiles and can accurately predict the impact of aging. There is support for instance-based aging, so that deals with differential aging. It is possible to set aging factors or aging stress profiles for each instance. As we have seen, SOCs do not have a single mission profile for their whole lifetime. They go through different mission profiles or multi-segment aging. And the aging aware solution from Cadence supports multi-segment aging. With these advantages, the designer is now in control of stress profile without making any assumptions in terms of aging context or having to go through a recharacterization whenever a new mission profile is needed for aging. There is also support for various flows like STA, ECO, etc. in the new Cadence aging aware solution. So the new solution helps avoid over design and health and hence leads to better PPA. Conclusion. Aging aware timing is important. We don't want to leave margins on the table and give a PPA for SOC. We also don't want to get exposed to silicon failures. The proposed solution from Cadence comprehensively covers aging aware STA and ECO. The solution is implemented in Cadence Liberate characterization flow and Tempest timing analysis flow. The proposed solution models various aging contexts. It supports instance-specific aging, non-uniform aging. So you have a lot of knobs for design engineers to explore. ARM evaluated the Cadence solution and has confirmed the accuracy of the solution. Cadence continues to work on improving the tool, and there will be support for HCI coming soon. Thank you so much for joining our presentation. If you have any questions, please do send us an email and we'll get back to you. Thank you so much.